So I've been talking about the classification of generalized cusps in projective manifolds. And I've been thinking about the simplest case. The generalized cusp is a non-compact manifold that's the product of a torus together with a ray. And there's a moduli space, which you can think of as given by the space of developing maps for these structures with an equivalence relation on it. So the topology comes from the topology on the space of developing maps, and then you take the quotient topology. So that's some abstract space. And actually, if you think about the possibilities for projective structures, real projective structures on a circle, all possible real projective structures on a circle, then that's a non-Hausdorff space. So for a couple of years, we didn't know whether the moduli space of generalized cusps was Hausdorff or not. It turns out it is. So you have a generalized cusp, then you have a holonomy homomorphism that maps a fundamental group into the affine group. And that homomorphism actually extends to a map of R to the n minus 1 into the affine group because the image is contained in a translation group. So the image of the extended homomorphism is what we call a translation group. It's a group of affine maps whose dimension is 1 less than the dimension of the affine space you're working in. And if you take the orbit of a point, you get a strictly convex hypersurface in affine space. And that strictly convex hypersurface is the boundary of a domain omega. So first theorem is that the holonomy homomorphism, so if you have a projective structure, you can take its holonomy. So that's a homomorphism, or an extended homomorphism of this vector space into the affine group up to conjugacy. And the claim is this is it's an injective map. It's also a topological embedding. This is a homeomorphism from the moduli space, this space of developing maps up to equivalence, onto a subset of this non-Hausdorff space. So that's an embedding. The next result is actually you can say what this space is. So a generalized cusp has a Euclidean metric on it defined up to scaling. So that is to say there's a positive definite quadratic form of determinant 1 on the vector space V. That's the similarity structure. In addition, there's a collection of vectors on V defined only up to permutation. So the dimension of V is n minus 1. There are n vectors defined up to permutation, and they're not arbitrary. They have the property that if you take the inner product with respect to this, with respect to the standard quadratic form, the inner product of any pair is a certain constant, a non-positive constant. So I kind of like negative numbers, I think. So independent of the pair of vectors. And the whole thing, these vectors, I mean, you've got an action of the permutation group on here, permutation of vectors. So this is a free action. And so actually, no. This is not a free action, but in any case, this tells you that this is actually homomorphic. This moduli space is homomorphic to a subset of Euclidean space, actually. So in particular, it's Hausdorff. And then specializing to dimension 3, you can encode this data here. You can encode this data as 3 complex numbers. The first complex number has positive imaginary part that encodes the quadratic form. And the second 2 complex numbers encode the other data. And they have this property that the modulus of R is at most 3 times the modulus of H. So that's the moduli space. And I want to summarize 100 pages that give you the proof. So are there any questions before I go on? Yes. Why is it defined on, your question is, why is rho defined on r to the n minus 1? Is that right? Yeah. Oh, yeah. Thank you. That is affine maps of r to the n.
So I guess my question was why you target the homomorphs from D, the affine space, the affine group as opposed to C to the n minus 1 to the n minus 1.
Right. So the ordinary holonomy maps the fundamental group into here. You think of a fundamental group as a lattice. So the holonomy maps this group into upper triangular matrices with positive entries on the diagonal. And so because of that, you can extend that homomorphism. This is a subgroup of this. And so this extends to that. Does that make sense? So I mean, you can think of the universal cover of the torus as r to the n minus 1. Sitting inside the universal cover, you've got this lattice. And so you think of the fundamental group as the integer points in the universal cover. The homomorphism is defined, the holonym is defined on the integer of the lattice, but it actually extends over to be a map of the universal cover into the affine group. Is that making sense? Yeah. Okay, so here's roughly how the proof of all this. So the proofs hinge on the fact that you can calculate everything. I mean, everything here is just polynomials, and with patience, you can calculate everything. Actually, there's a bit more to do because in some cases, you've got to think about topological spaces and quotient spaces and topologies. But anyway, the bottom line is a lot of things end up being equal. There are various descriptions of the moduli space, and they're all equal. And at the end of the day, the proof is you just calculate everything. But in any case, so the beginning of the story is that if you have a point in the Weil chamber with these parameters psi1 through psi n, then I described a translation group, a subgroup of the affine group that depends on these parameters. And there were various types. There was a diagonal block in the top left corner, and in the bottom right corner, there was a kind of unipotent block. And so if you pick a point in the Weil chamber, you get a subgroup of the affine group, and there are various types. There are n different types. Type n is diagonalizable. Type 0 is a unipotent group, the standard group of parabolics in hyperbolic space. You get finitely many types of translation group. Given such a translation group, there's infinitely many because you've got all these parameters. You take a lattice in one of these translation groups, and that lattice gives you a generalized cusp. What is a generalized cusp? Well, take this translation group. It's a group of affine maps, orbit the base point in Euclidean space. You get a hypersurface, and that hypersurface bounds the domain. It picks out a domain of this convex set in Euclidean space. If you take the group of affine transformations preserving this domain, that's a group called G psi. And inside that group, there is a stabilizer of a point. That's the orthogonal group, depending that stabilizes the base point. So in particular, for type 0, we're talking about a horosphere in hyperbolic space. The orthogonal group for type 0, that was when psi is 0, would be the orthogonal group acting on the horosphere. So that would be the orthogonal group in dimension n minus 1. In general, depending on what, and at the other extreme, when psi is diagonalizable, the orthogonal group is going to be a subgroup of the permutation group acting on these guys. So you get this compact subgroup, the stabilizer of a point, it's inside of here. Now, there's a Euclidean metric on the boundary of omega coming from the second fundamental form. That Euclidean metric is beta. And this group is a group of isometries of beta. So that means that this group fits into a short exact sequence. It maps onto the orthogonal group for psi, and the kernel of that map is the translation group. And so we see that the group of affine maps that preserve omega psi is a subgroup of the group of isometries of Euclidean n-1 space. It's got the entire translation group, but it's only got a subgroup of the orthogonal group. And in general, I've been talking about torus lattices, but in higher dimensions, they're more complicated cusps, and they're just lattices in here. So from this, one sees that if you fix a psi, the possibilities for lattices correspond to cosets of this orthogonal group in the special linear group. The point is that if you take an element in SLN-1R, you can compose it with one fixed homomorphism of V into T psi, and you get a new one. And those give you different lattices, different generalized cusps, except that if you rotate one of these things by an element of this orthogonal group, the geometry doesn't change. So its lattices for a fixed psi are this set of left cosets. So this is a manifold. Now, if you want to know about all the lattices for fixed type, you take the union of all these over as psi varies over a fixed type. You're taking a union of manifolds of some dimension. And that union, if you think about it, you take the product, or you take all parameters of a fixed type. So if you're dealing with type 3, you take 3 positive numbers, and you take the product of this interval and the moduli space for fixed type, and then you have to quotient out by the action of the permutation group. So this permutation group acts on here. It also acts on here. It ends up being a free action, and the quotient is a manifold. So at this point, one discovers that if you fix a type, then the set of moduli of fixed type is a manifold. And so the entire moduli space is the union of these manifolds. And the question was, is this Hausdorff? What's the topology on that union? So the answer was to parameterize translation groups a new way by blowing up the Weyl chamber. So instead of having a single parameter in the Weyl chamber called psi, now we've got a pair of things. We've got a parameter lambda in the psi chamber, together with these extra numbers kappa, which describe a direction of approach towards a facet of the original Weyl chamber. So it's a kind of blow up of this in the sense of algebraic geometry. And the point about this is that I wrote down a different family of translation groups. For each lambda and kappa, there's a translation group. And this family varies continuously in both lambda and kappa. So there's a continuous map that takes as input a lambda and kappa and gives you as output a translation group. And those translation groups, some of them are conjugate. The conjugacy class doesn't depend on kappa. It only depends on lambda. And so this translation group is conjugate to one of the T psis. And the relationship between the lambdas and the psis of the lambdas are 1 over the square roots of the psis. So, so that's the kind of, this is the key to showing that the moduli space in total is a connected space, a Hausdorff space. So the definition of the space we're looking at is developing maps up to affine equivalence and deformation retraction. And so there's a bit of topology work to show that this space maps homeomorphically. The holonomy map is a homeomorphism onto a subset of the space of representations mod conjugacy. So moduli space is homeomorphic to a subset of a non-Hausdorff space. Next, one computes the similarity structure. This is the character of the representation. So if you have an irreducible representation, it's determined up to conjugacy by the character. Our representations are the opposite of irreducible. I guess they're reducible. And they're determined by, well, not just the character, the extra information you need because they're reducible turns out to be just given by the similarity class of the Euclidean structure. So algebra tells you that a generalized cusp is uniquely determined by the similarity structure and the character. And the character lives in the trace variety, an algebraic variety. So we've got an injective map now that sends a generalized cusp to a point in this, in this nice space. And so you actually show that this is the map that sends a generalized cusp to this data actually gives you a homeomorphism from the moduli space into a subspace of this space. And so now you want to know what the image of that map is. Another thing you see, which is kind of nice, so earlier on I said, so given one of these generalized cusps is this orthogonal group, the group of affine maps that preserve a point on the domain. And one discovers by direct computation that what we've got is we've got a similarity structure on the vector space, Euclidean metric up to scaling, and this character is a function on the vector space. And the set of affine maps that fix a point is exactly the set of linear maps on the vector space that preserve both the similarity and this character function. So one thinks of this as a geometry on the boundary. And you can make that more concrete. So the character is determined by the weights. And the weights, each weight is an element of the dual vector space. And you can think of the dual vector space as the cohomology of the generalized cusp with real coefficients. And of course, the V is the one-dimensional homology. So you can turn the weights, these are Lie algebra weights, so they're elements of the first cohomology. You can use a quadratic form to turn them into vectors. And so you can think of these vectors as elements of the first homology. And then what is the condition that gives you on the holonomy, on the character that gives you a generalized cusp? Well, it turns out by direct computation that you get this interesting equation that if you take a pair of distinct vectors here, they're in a product using beta is always the same thing, a certain non-positive constant. Then I talked about the shape invariant, that if you take the 3-jet of the graph of the boundary of the domain, you get a quadratic and a cubic. The quadratic is the second fundamental form. The cubic turns out to be, well, you can express the cubic in terms of the weights. It turns out to be the sum, well, 1/3 of the sum of the cubes of the weights divided by this number. So the cubic is basically encoding the weights. And with an enormous amount of work, you can show that if I tell you the cubic, you can actually recover these weights. So if I tell you the sum of the cubes of certain linear polynomials, you can actually recover the linear polynomials in this particular situation. So, so that is actually the proof that the shape invariant uniquely determines generalized cusp, because from the cubic, you can recover the weights. When you specialize to dimension 3, the cubic is a cubic polynomial on the plane. So it's got basis x cubed, x squared y, xy squared y cubed. It's a vector space of dimension 4. That vector space of dimension 4 is a direct sum of two two-dimensional vector spaces, the harmonic polynomials and the radial polynomials. This is a decomposition that's preserved by the action of SO2. The harmonic polynomials is a vector space spanned by these two polynomials. The radial polynomials, vector space spanned by these two. A harmonic polynomial can be written as the real part of hz cubed, where h is a complex number. So you can think of the harmonic polynomials as a complex number. Similarly, the radial polynomials are the real parts of rz times the absolute value of z squared, where r is a complex number. So you can think of these as the complex numbers and those as the complex numbers. And so, in other words, we can think of cubic polynomials on the plane as the same thing as a pair of complex numbers. If you give me a pair of complex numbers, here is a cubic polynomial on the plane. Now, the condition on the weights, when you do the algebra, turns out to be the modulus of h is less than or equal to 3 times the modulus of r. And so that's the moduli space of generalized cusps in a three manifold. I went a bit quickly. There's 100 pages published about that. Any questions on that? Yeah. Oh, yeah. Which line? Number 11. Number 11. Oh, why this tells you the geometry and the boundary? Well, it's a computation. So at this point, we know what all the affine groups are. And if you compute this and you compute this, you see it's one-to-one. That's the proof. It's a computation. Does that answer the question? Yeah. So if you give me a generalized cusp, you have a representation. It's only defined up to conjugacy. So the whole point is to come up with conjugacy invariants of a representation. The character is an obvious conjugacy representation, but this quadratic form is a less obvious conjugacy invariant. Does that answer the question? Any other questions? Okay. So now I want to talk about deformations. And so the next step, so if you have a properly convex closed manifold, sometimes you can deform it. And there's a theorem that says that the set of properly convex projective structures the set of strictly convex projective structures on a closed manifold is a union of components of the character variety. And so this is in dimension 2, one's thinking about pitching components. So we'd like to extend this result to the non-compact case. And you have to add conditions. In particular, in dimension 3, in studying deformations of three manifolds, it's easier to come up with examples of deformations of a three manifold which isn't compact, something like a knot complement. There are fewer relations in the group to satisfy, so it makes the computations easier. And so you discover paths of representations of the fundamental group of the three manifold. And you maybe know, you start maybe at the hyperbolic structure, which is a strictly convex structure, and then you deform it. And you'd like to know that there are strictly convex structures or properly convex structures all the way out along this path. So you've got this path of representations, but you want to know that they correspond to geometric structures. And so you want some extension of this theory from the closed case to the non-compact case, that when you change the homomorphism, there's a corresponding new geometric structure. And so that involves understanding the geometry in the ends, that is the generalized cusp, and then having a deformation theory. So I'm now about to talk about the deformation theory. The basic result behind a lot of this stuff is this remarkable Benzacree compactness theorem. And so we've been talking about properly convex domains in projective space. And properly convex domains, if you take a properly convex domain in projective space and a point, that's a pair. And the collection consisting of pairs of properly convex domain, point in the interior of that domain, that's a compact family. Benzacree's theorem. And one way to say it is that every dimension, there's constant, the Benzacree constant, with the following property. If you've given a properly convex domain in projective space and a point in the interior of that domain, then there's a projective transformation which will send that domain to a subset of Euclidean space that contains the unit ball around the origin, and it's contained inside the ball of radius beta n around the origin. And beta n is a constant. So all the properly convex domains can be sent to one of these things, and the point you chose is sent to the origin. And so a Benzacree domain then is a properly convex set that's been put into this nice position in Euclidean space. Once you know that, you get the following. So this is saying that the set of properly convex domains, comma, point in the domain is compact set. Given a domain omega and a point in there, you might ask about the subgroup of projected transformations that move that point a distance less than or equal to a constant d. And well, if you restrict to thinking about Benzacree domains as this compact family, then all the projected transformations of all such domains that move the origin a distance at most d is a compact subset of SLN plus 1R. And that's just compactness. It's once you know this, compactness tells you this is compact set. So domains are compact, and projected transformations that don't move a point very far are compact in this sense. Now, there's a basic algebra fact about GLNR. There's a neighborhood of the identity called Z in GLNR with the property, if you take two elements in that neighborhood and take their commutator, they're a lot closer to the identity. So there's this small neighborhood of the identity where the commutator maps a contraction. It moves points closer to the identity. So a consequence of that is if you've got a discrete group, subgroup of GLNR, because it's discrete, if you think about the subgroup generated by the elements in this small neighborhood, that's a nilpotent group. And the reason is that, I mean, if you keep taking the commutators of elements in this discrete group, because it's discrete, you've got to hit the identity. And so that tells you, because iterated commutators are giving you the identity that this group of small elements is nilpotent. So in a discrete group, the subgroup generated by small elements is a nilpotent group. So this leads to the Margulis lemma. So the Margulis lemma, what is that? So it's a theorem about properly convex manifolds. And so in every dimension bigger than 2, in every dimension bigger than 2, there's a positive Margulis constant. And the deal is, if you have a properly convex manifold in this dimension and a point in there, you can think about the loops starting and ending at that point, whose at length is at most the Margulis constant. So that will be some subgroup of the fundamental group. Might be it might just have the trivial element in it. You get some subgroup, the group generated by short loops. And the point about this subgroup is it's virtually nilpotent. There's some subgroup of finite index that's nilpotent. And the proof is, well, once you've got the stuff on the previous slide, it's a standard proof of Margulis lemma that you can find, for example, in Thurston's book. And so what is the proof? So, okay, well, I've got to give you the Margulis constant. So how am I going to do that? We've got this neighborhood of the identity in PGLN plus 1R with a property that you had on the previous slide. So this is the group that contains all projected transformations that move the origin in a Benzacree domain of distance at most 1. And so I'm going to think about the set consisting of elements in that should be pi1 of m, or the holonomy of pi1 of m. I'm going to think about elements in the fundamental group of M, those elements gamma, that move this tiny Zassenhaus neighborhood somewhere where it intersects this compact set. So, there's going to be some finite number of elements in pi1 of m, So the translates of the Zassenhaus neighborhood meet this compact set. So if I'm going to take mu, the Margulis constant, to be 1 divided by the number of elements that have this property. And then I'm going to take W to be, this should be the set of elements in par 1 of M, or the holonomy of par 1 of M. I'm going to take the elements in the fundamental group of M that move, and that, well, X here is the base point. So omega is the Benzacree domain. We've put this domain in, made it into a Benzacree domain, and it's moving the origin at most this constant mu that I've just told you. So that is the subgroup of the fundamental group of M, consisting of loops whose length is less than the Margulis constant. So I'm going to take, so that means gamma is the group generated by these elements. These are the elements that are moving the origin at most the Margulis constant that I've defined. And then because these elements move the origin a distance at most mu, if I take a product of at most m elements in this subset, they will move the origin at most m times mu. And m times mu is 1, so the words of length m in these elements will all be, and that should be in the set S. So this set W, if I take words of length m in this set W, I'll be in the set S. And then the deal is if I take the subgroup, so this subgroup gamma is generated by elements in W. These are things that move the origin at most mu. If I take the subgroup of gamma generated by elements in the Zassenhaus neighborhood, that's a nilpotent subgroup. So the claim is that this group has got finite index in the group I first thought of. So why is that? Well, if that's not true, there are m+1 distinct cosets of this subgroup in gamma. Now then, the claim is that these cosets can be chosen to be words of length at most m in this set of elements W. And then once you know that, it follows that all these elements are in W to the m, and so they're in, I hope my notation is right, that that means they're in S. Dear. So all these elements are in S, and that's a contradiction to the number of elements that were in S. So why can I choose these cosets all to be words of length at most m? Answer, I can start with my first coset will be the identity element. That's in here. So there's one element coming from a word of length 0. Now let's think of words of length 1. Well, if there are no words of length 1, that would mean that this is the trivial group and we're done. Otherwise, there is a word of length 1. And so, sorry, I'm saying it the wrong way. So I start off with the identity element times gamma z. If there's another coset, that second coset, there must be a second coset that is a generating element times gamma z, because if all the generators, I mean, W is a generating set for gamma, if all the generators times gamma z give you the same coset gamma z, then that would mean gamma equals gamma z. So when I go to words of length 1, I have to pick up another coset. And when I go to words of length 2, I have to pick up another coset. Otherwise, gamma would be finite. And so every time you increase the word length by 1, you have to pick up at least one more coset. And so that's the Margulis lemma. And so I didn't explain this proof very well, but it's in. So the Margulis lemma follows just basically from the Benzacree compactness theorem. and the existence of Zassenhaus neighborhoods. Okay, so next, the thick decomposition. So here's a question I don't know the answer to. Maybe somebody does. You've got a properly convex domain, omega. You've got a projective transformation that preserves omega. Think about the set of points in omega that had moved a distance less than r by this group element. And the question is that always a convex set? Is it even connected? I don't know. Anyway, and that's kind of relevant to what comes later. So this is, as far as I know, this is an unsolved question, very basic question I don't know the answer to. Suppose we've got a properly convex set, a properly convex manifold, and a point X in the manifold. Then the injectivity radius of that point is the radius of the largest embedded ball. So this means radius in the Hilbert metric. It's the radius of the largest embedded open ball in the manifold with center X. And then the epsilon thin part of M is all the points in M where the injectivity radius is less than or equal to epsilon. So this is a subset of M depending on some constant epsilon. So given a positive number epsilon, if M is any properly convex manifold, then there's a properly convex manifold which is the product of M times a circle, and the entire manifold N is epsilon thin. So there is nothing interesting to be said about the epsilon thin part of a properly convex manifold. But for a strictly convex projective manifold, there is something interesting to be said, the thick-thin decomposition. So if M is a strictly convex manifold, then it's a union of two bits, A and B. And as indicated here, so B is the thick part, and the A has got various components, it's the thin part. So the property we have is that A contains all the points where the injectivity radius is very small. Very small means less than this multiple of the Margulis constant. All the very points with very small injectivity radius are in A. Not only that, if X is in A, the injectivity radius is pretty small. It's less than half the Margulis constant. And then the interesting thing is we can say what the thin parts are. The thick parts, they're complicated, but the thin parts are of two kinds. One kind is a solid torus, the so-called Margulis tube. And the other kind is a cusp. So a cusp here means not a generalized cusp. A cusp means something with parabolic holonomy. It means it's a product of a manifold of codimension 1, an array. It's a properly convex manifold, and it has parabolic holonomy. So that is a cusp rather than a generalized cusp. And the deal here is that C might not be compact. I've been talking about maximal rank cusps where this is compact. But in general, you have this thick-thin decomposition. The manifold B needn't be compact. The boundary of B needn't be compact. You can have these cusps. So that's, and then A is called the thinnish part, and B is the thickish part. So, yeah. So this is, this comes, yeah, sorry.
Change the condition of strictly convex to properly convex.
Yeah, if you change this to properly convex, nothing like this is true. You can't say anything about the topology of the thin part because of this. Or to be more precise, I think maybe you can, well, yeah, never mind. There's no corresponding statement like that for the properly convex. So in Riemannian geometry, there's a thick-thin decomposition if you have metrics of pinched negative sectional curvature. So this is inspired, you know, so there's this strictly convex is a bit like pinched negative sectional curvature. properly convex, you allow curvature 0. And there is like allowing curvature 0. And then this doesn't work. Okay, so the basic idea is if you've got a strictly convex structure and you change the holonomy a little bit, do you have a new strictly convex structure? The deformation theory. So I've got some manifold, and I'm going to be thinking that a rep par 1 of M means all the homomorphisms of a fundamental group into PGL n plus 1R. So M is probably an N manifold. The manifold dimension N. So I'm looking at the homomorphisms. That's what rep par 1 of M is. And then rep CE of M, this is a subset of this. And it's a subset of holonomies of, of properly convex structures on M with the properties. So I'm going to allow these manifolds to have boundary. And the boundary has to be strictly convex. And in addition, every end of M is a generalized cusp. I'm going to be thinking about manifolds of this type. And so CE is to make us think about convex ends. So having convex boundary component is you kind of got a convex end, and then these generalized cusps are kind of convex ends as well. Although that's convex outwards and that's convex inwards. But anyway, so the notation, these are the representations we're interested in. What can we say about the holonomies of properly convex structures where the ends are generalized cusps? And there's a concept of a virtual flag group. So what's a virtual flag group? It's a subgroup, it's a group of matrices. It's a virtual flag group. What does that mean? It means it contains a subgroup of finite index that's conjugate into the upper triangular subgroup. Another way to say it is a subgroup of finite index that preserves a flag. So the theorem is the following. So we've got some compact connected manifold with boundary. And then you delete some of the boundary components. The boundary components we're going to delete are going to be tori. So we've got this compact manifold. Maybe it's a 3 manifold. Maybe it's got a torus boundary component. We're going to take some of the boundary components and remove them. So M is going to be the compact manifold with these boundary tori removed. And so the fundamental group of M and the fundamental group of N are the isomorphic by the inclusion map. So the theorem is that the representations we're interested in, so this is rep CE of M. So we're thinking about properly convex structures on M where the ends are generalized cusps. This is an open subset of, you think about representations of the fundamental group of N. That's the same as the fundamental group of M. You think about representations with a property that the holonomy of the boundary components you deleted are virtual flag groups. In other words, the ends of the manifold, there's a restriction on the holonomy. Namely, the holonomy has got to be a virtual flag group. Another way to say that, in the case where these are tori, another way to say it's a virtual flag group is to say if I take some representation, it's got to have the property that if I take an element in the fundamental group of one of the ends, every eigenvalue is a positive number. So that's another way to say virtual flag group. So that's the openness condition. And then if we now assume that this manifold we're dealing with doesn't have any boundary, so it's a non-compact manifold and there's got ends at a generalized cusp, but there are no boundary components. And we add this algebraic condition that the fundamental group doesn't contain a non-trivial normal abelian subgroup. In that case, the representations of holonomies of these properly convex structures, where the ends are generalized cusps, is a union of connected components of this space. And this space is actually a semi-algebraic variety. It's defined by polynomial inequalities, very explicit polynomial inequalities. So in this case, you have this nice result that the properly convex structures, you kind of know what they are. And so this was motivated by examples. I mean, people had examples of for three manifolds, not complements of representations. One wanted to know that they corresponded to projective structures, and this theorem says they do. Sorry?
So in the fundamental group of the manifold N, yeah. Well, hyperbolic group?
Not here, no. Yeah, no, here it's not. No. So what I want to do is sketch some of the ideas here. I'm going to think about the vector space V, this real vector space dimension n+1 with an inner product on it. And then I'm going to have a properly convex domain. Well, I've lifted to the double cover of projective space. I'm thinking about this properly convex domain as living in the n sphere given by this inner product. So the n sphere I can identify with the double cover of projective space, with so-called positive projective space. So this is a properly convex domain sitting in, if you like, an open hemisphere in here. Then I can take the cone on that domain. I can take all positive multiples of vectors in this set. So that will give me some, here's the sphere. I've got this domain omega. And then I've got the cone on omega. So this is all sitting in Euclidean space. Then there's the dual cone. So the dual cone is a set of dual vectors with the property that they evaluate positive on, well, the closure of this cone with the origin removed. So that's a dual cone sitting in the dual vector space. And if I projectivize it, I get a dual domain in the projectivized dual space. And if I dualize twice, I'm back where I started. So given a properly convex domain and this inner product, there's a dual domain, and dualizing twice is back where you started. The domain is called C1 if there's a unique supporting hyperplane. So if I have this region here, there's more than one supporting hyperplane at this point. So this domain is C1 except here at one point. It's a proposition that a domain is C1 if and only if the dual domain is strictly convex. So line segments in the boundary of the dual domain correspond to non-C1 points. And next time, I'll start talking about deformation theory.
Some examples of which
Examples.
Having some generalized.
Yeah, right. So I mean, if you take the figure 8 knot complement, it's got a complete hyperbolic structure. The end is a cusp, and then there are deformations of that which are properly convex, and the end is a generalized cusp. Is that what you wanted to know?
Then